Let's look at an example of a function we can define in two different ways, one of which is much more efficient than the other. Exponentiation is built into Python. I can raise one number to the power of another. But let's write an exponentiation function recursively. Our goal will be to have it so that one more multiplication lets us double the exponent that we're using in exponentiation. Here's an implementation that does not meet this goal. This says to raise b to the power n, if n is 0, return 1. Otherwise, multiply b to the n minus 1 by b. This is a correct definition, but if I double n, I have to do twice as many multiplies, because each time I make a recursive call, I'm only reducing n by 1. And this function's implementation corresponds to the following mathematical definition for b to the n. But this is not the only mathematical definition of b to the n. Here's another one, more complicated, but the additional complexity will also give us additional efficiency. This says that b to the n is 1 if n is 0, and then has two different cases for whether n is even or odd. If n is even, then I can raise b to the 1/2 n power and square that result. So if n is 16, I raise b to the 8, and then I square b to the 8 to get b to the 16. If n is odd, then I use the definition I had before. Here's an implementation. This is a more efficient version of exponentiation that has two different recursive cases depending on whether n is even, in which case you square the result of exponentiating b and n divided by 2, where I know that n is even, so floor division will give me the exact result. And if n is odd, then I use my old definition. This is not a tree recursive function, even though I see two different calls to xfast in the body. Only one of them is ever called. So this is an instance of linear recursion. And sometimes the problem size is reduced by half, meaning one more multiplication, in this case by calling square, lets us double the size of the problem that we're handling. And xfast runs faster. Let's take a look. This environment is called a Jupyter notebook. You can read about them online. It's a common way that people use in order to execute Python code when the output is a graph or a chart. So here's our definition of exp the slow way. And something that's built into this notebook environment is that we can time how long it takes to run something. So if I raise 2 to the 400th power, the time it took was 2 milliseconds. If I raised 2 to the 100th power, it only took me 100 microseconds. But if I run it again, I'll get a different number each time. So if I run it a bunch of times, I see it hovers around 100 microseconds. 2 to the 400th power tends to hover around 200 microseconds. Running it a bunch of times this way is inefficient, so I've written some code to run it a bunch of times, using the built-in timeIt module, which can repeatedly call something, and in this case we're going to compute the median time that it takes to execute some line of code. And here's the result. 2 to the 200th power takes a little less than half a millisecond. 2 to the 400th power takes a little less than 1 millisecond. This looks like a straight line. The term we use to describe this is linear. The time that it takes to compute 2 to the n under this implementation is linear in n. Now it's a little bit bumpy because all kinds of interesting things are happening inside of a computer, but the word linear is used even if there are slight deviations from the line to describe the general trend that appears when you plot the time it takes to compute something as a function of the input size. And here's the fast definition. We can draw the same plot and we'll see that the overall numbers are quite a bit smaller. For 1600, instead of taking 4 milliseconds, it takes only 0.04 milliseconds. Also, the shape of the curve is different. This shape is called logarithmic. The difference between going from 200 to 400, in this case, is just about 0.002. And what about the difference between going from 400 to 800? Well, that's another 0.002. Going from 800 to 1600 is another 0.002. Every time we double the input, it just takes a constant amount of extra work. And that's because we're making recursive calls on n that's only half the size. That's called logarithmic time. So to summarize, a linear time function requires one more unit of work for every one bigger n. That means doubling the input doubles the time. And 1,000 times the input takes 1,000 times as much time. 1024 is 2 to the 10th power. Logarithmic time is much better. Doubling the input just increases the time by some constant. And 1,000 times the input just increases the time by 10 times that constant. So it takes 10 times as long to do 1,000 times as much work. And these terms linear and logarithmic are used to describe the general shape of time as a function of input size, even if there are wiggles and bumps along the way.